All right, welcome to today's video about projectiles. The objectives are here on the screen. By the end of the video, you ought to understand what a projectile is, be able to give examples. You should be able to apply the two big rules of projectiles, and most importantly, be able to use those rules to solve problems dealing with projectiles. All right, so here we go. A couple quick definitions. Let me embiggen the screen here. Got a couple notes left over from the last time I used this. All right, so here we go. All right, so far we have seen how force can be used to change the speed of an object, right? You can push an object to make it go faster, push an object to make it go slower. Last chapter we saw how force, or not even last chapter, last section, we saw how force could be used to change the direction of an object, right? If it's going in a circle, then your force is changing the direction. All right, but sometimes force will change both the speed and the direction of an object. All right, and a projectile is one example of that. All right, so our textbook definition of a projectile is any object in free fall. All right, usually, however, when you talk about a projectile, you're talking about an object that's in free fall while it has horizontal motion. Okay, so if I drop this ball, it's got vertical motion, right? Technically a projectile. All right, but usually when you talk about a projectile, you're talking about something that has vertical motion as well as horizontal motion. Okay, so projectile, okay, or whatever. All right. So long story short, up until now we've dealt with problems where an object has been thrown either up or dropped or thrown down. Now we're going to deal with what happens when something is thrown at a weird angle like that. Okay. So in all cases, regardless of what direction your projectile is sort of launched in, the only force on it while it's in the air is gravity, right? So it's in free fall. All right. And as usual, to be in free fall, we're going to assume that there will be no air resistance. All right. So remember, when you throw that projectile, when you throw your object, the force of gravity does a couple things. One, it causes it to change directions, right? If you throw the projectile this way, it doesn't kind of keep going that way forever, right? It changes direction and follows this parabolic path, right? Pretty happy with that parabola I just drew there. All right. Secondly, it changes speed, right? Because as it goes up, it slows down, slows down, slows down, slows down, and then eventually it comes down and speeds back up again. Okay? So there you go. Our force of gravity causes our projectile to change direction, so it doesn't go in a straight line, and it changes speed. All right? All right. I guess the next thing to be aware of is this. Remember, velocity is a vector, right? And so it's going to have direction, all right? And in particular, it's going to be really important when we deal with projectiles because the projectile has motion both horizontally and vertically. Okay, so if you imagine, kicking a football, let's see if I can draw another parabola as good as my first one. All right, so there's the path that my football follows. All right, so at any given instant, the projectile has a velocity vector, right? So here's my velocity vector. Okay, now that velocity vector, because it's at a weird angle, we need to resolve it into components, like we did with forces when we did nonlinear forces. All right, and so, this velocity has a horizontal velocity at that instant, and it's got a vertical velocity at that instant, okay? And it's traveling at some angle theta, okay? So these components here, these triangles, are going to be very, very important. So just something to be aware of, all right? So we will be talking about an object's horizontal velocity and its vertical velocity, all right? Which brings us to the two big rules of projectiles, all right? If you understand these two rules, you can solve any projectiles problem I give you, all right? And basically what you guys are going to find is there's no new equations here, all right? It's basically just manipulating the equations from first chapter and a little bit of Newton's first law, I guess, or maybe first two laws, okay? All right, so here we go. So big rule number one. So it turns out that the horizontal velocity of any projectile will remain constant. Okay? How quickly an object moves from left to right does not change. Okay? And it's just an extension of Newton's first law. So the idea is if I throw, a football through the air, so here's my football. That's the worst football ever drawn by a human being. as it flies through the air, the only force on it is gravity, right? Okay, and so the idea is horizontally, our net force horizontally is going to be 0, right? Okay, the net force on it horizontally is 0. And that means that we're not going to have any acceleration horizontally. And as a result, the rate at which this football is moving horizontally is going to be constant. Okay? So what that means is every second the projectile is in the air, it's going to move the same distance horizontally. All right? So here's our example. It says, suppose a car drives horizontally off a cliff at 20 meters a second. If it's in the air for 4 seconds before landing, then what? Well, let's see. So let's draw this. So here's our car. Happy little car driving along at 20 meters a second. So notice, initially, all of the car's motion is horizontal, right? There's not any motion vertically. The car is driving horizontally. So this is both the initial velocity, it's also the horizontal velocity of the car, all right? So what that tells us is that for every second that the car is in the air, it's going to travel 20 meters. So here's the path the car follows. We'll draw it in red. All right? So what that means is it's traveling at 20 meters a second. So our horizontal displacement is going to be Vx times t. It's traveling 20 meters every second for 4 seconds. That means it's going to land 80 meters away. Okay, so what that means is it goes 20 meters in the first second. So after 1 second, here's the car. After 2 seconds, there's my car. After 3 seconds, it'll have gone another 20 meters. And after 4 seconds, the car will have hit the ground and it will have gone a total of 80 meters. Okay? But the idea is because the horizontal velocity is constant, it goes 20 meters every second. Okay? Now keep in mind that we are ignoring air resistance here, right? But even in the case of air resistance, you can still see this. All right? So I'm going to edit in a video. Okay. All right. So in that example, that's basically the same as this. We've got here was our airplane. Right? So the airplane was flying along at some velocity horizontally. Okay? And a moment later, here's the airplane. All right? And the idea is the bombs, or whatever those little things were that were falling out of it, were always under it, right? So when the airplane was here, the bomb was here. When the airplane was here, the bomb was here. A moment later, the airplane will be here. And the bomb will be right here, right? And the idea is both the airplane and the bomb are traveling horizontally at the same velocity, and so the bombs are always directly underneath the airplane. So from the perspective of the airplane, it looks like the bombs are going straight down, right? Okay? But from a side perspective, watching them, the bombs are actually going to follow a curved path like this, just like the car driving off of the cliff. All right? If the bombs, or if the planes wanted the bombs to actually drop straight down, like so literally, so they landed directly beneath the point where the plane released them, they would actually have to fire them backwards. All right? Let me show you that by way of another video. Okay?
I have a feeling that we are very close to a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air. It stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector edition! Woo! We canceled out velocity!
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
Okay, so that is the first rule. All right, horizontal velocity of any projectile always remains constant. Okay, big rule number 2. So this is the one that students tend to have a slightly tougher time with. Big rule number 2 says this: any projectile will always fall with a vertical acceleration of negative 9.8 meters a second squared, in other words, the acceleration of gravity, regardless of the horizontal motion that it has. So in other words, how fast an object is moving horizontally has nothing to do with how quickly it drops. Okay? Again, it's an extension of Newton's second law, right? Because once your projectile is fired, so here's a ball that we've just thrown, right? Once you fire it, the only force on it is gravity, right? And so our net force is going to be the force of gravity, and so the acceleration is the acceleration of gravity, right? Okay? So our net force vertically is our force of gravity, which means our vertical acceleration is the acceleration of gravity. So every second, the vertical velocity decreases by 9.8 meters a second squared. Okay? So to paint that into an example, suppose we've got 6 cars that drive horizontally off of a cliff that's 44.1 meters tall. Okay? Which one's going to hit the ground first? All right. Well, so 44.1 meters. Where did I get that? Well, so let's do this. Let's suppose we've got car A that we're just going to drop off a cliff. All right, and it's going to fall down. I'm going to actually call this delta y. Historically, we would have called that delta x, but now because we're moving vertically, let's call it delta y. All right, here's what we know. We know that our initial velocity is 0. We know that our delta y is negative 44.1 meters. We know our acceleration vertically is going to be negative 9.8 meters a second squared. So delta y equals 1/2 at squared plus vit. All right. So let's see, negative 44.1 equals 1/2 negative 9.8 times t squared plus 0. And the time here ends up being, I think it's 3 seconds. Yeah, that's totally 3 seconds. Sorry. Okay. All right. So what this is telling us is that if you drop an object from rest, it will take 3 seconds to fall down 44.1 meters. Okay? So car A is going to hit the ground in 3 seconds. Okay? Now, what rule number 2 tells us is that cars B, C, D, E, and F that are traveling horizontally are still going to take 3 seconds to fall. The only difference is the faster they're going, the farther they go this way during those 3 seconds. Okay? So let me kind of clean up the board here. So here's the deal. So here's my cliff. I'm going to give myself some more room here. Okay, so here's the cliff, right? Okay, so car A is going to go 1, 2, 3, boom. Okay, now car B is traveling at 2 meters a second. So car B is going to go 1, 2, 3. Because it's going this way at 2 meters a second, which means it's going to land 6 meters away, right? 2 times 3. Car C is going at 10 meters a second. So that means it's going this way at 10 meters a second, so it ought to land in 3 seconds 30 meters away. So car C is going to go 1, 2, 3 and land 30 meters away. Okay? Car D is going to land 150 meters away. So it's going to go 1, 2, 3 and land way over here off of the board. Okay? But all of these cars are all going to hit the ground in the same time, 3 seconds. The rate at which they fall is not affected by how fast they're moving. Even this one that's going, what is this, 1,000,000 meters a second will still hit the ground in the same amount of time if you ignore the curvature of the Earth, which is a separate issue. All right, and this is really clearly illustrated by a Mythbusters video in which they simultaneously drop and fire a bullet from the same height, and you can see them hit the ground at the same time. All right, and I'll edit that in now.
Needed to match the solenoid.
Everything's hot. Let's do it.
And after a few test fires and a bit of fine-tuning, it works.
Bullet leads done. Oh, it's good. It's good. It's 1/3 of a millisecond difference.
Wow.
That's freaking perfect. Let's go do this full scale.
Okay.
Which means rolling up the room 360 feet to stake out a drop zone.
Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here.
Okay.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves and a victory for physics.
All right, so at this point we've learned two rules, right? We've learned that the horizontal velocity of any projectile is constant, and we've learned that the rate that an object falls at is negative 9.8 meters a second squared, regardless of how fast it's going horizontally. All right, so there are a lot of variables you got to keep track of here. All right, so here's the deal. Suppose we've got a projectile that's launched, whatever, maybe it's a soccer ball that gets kicked through the air. Okay, so there are a whole bunch of variables you got to keep track of. All right, so here's this. So the velocity that it's fired at, I'm going to call this VI. So at this instant when the ball is first fired, there's an initial velocity. Okay, that velocity is going to have a horizontal component and a vertical component. The vertical component changes though, so I'm going to call that VIY. All right, and this is my initial angle, right? Okay. Now, as the ball flies through the air, the velocity changes. So after some amount of time t, there's going to be a final velocity. So maybe the next time I look at the ball, it's over here, right? So at that instant, how much time has passed? Time t, whatever, some amount of time. And at that instant, it's now going this way with some velocity, which I'll call vf. All right, so at that instant, there's a new velocity triangle, right? So it's going this way with some velocity, vf. At that instant, it's moving horizontally. Remember, big rule number 1 tells us that this horizontal velocity and this horizontal velocity are the same, but my vertical velocity has now changed. So this is my VFY, my vertical component of velocity, and there's a new angle, theta f. Okay? So what I want you to gather out of this drawing is this. There is a different sort of velocity triangle at every point throughout the object's motion, okay? Because the velocity is always changing, right? Okay? Now, the other thing we need to be aware of is displacement, and we're now going to use two different types of displacement, okay? There's horizontal displacement, which measures how far the projectile has gone horizontally, and there's vertical displacement, which measures how far the projectile has gone vertically. All right, so basically your vertical displacement just amounts to the height of the projectile, okay? And your delta x, your horizontal displacement, is how far it's gone, okay? All right, now, because of our rules, it turns out there's sort of a clear set of equations that we're going to use, okay? So way back, at the beginning of first chapter, we learned a whole list of different equations, okay? We learned these linear equations, okay? And they're divided up this way for a reason. These were the equations that we used usually if the acceleration was 0. And these over here were the equations that we used if the acceleration was not 0, right? You can see all of these ones have at least acceleration or some VF and some VI that are independent of each other, right? Okay? So these ones are the ones that we are going to use to describe the horizontal motion of a projectile. And these variables are going to be the ones that we're going to use to describe the vertical motion of a projectile. All right? So here are the equations that we're going to use, okay? Horizontally, really, this is the only equation that we've got to deal with the horizontal motion of an object, okay? The horizontal displacement is equal to the horizontal velocity times the time. But vertically, there's a lot more going on, right? Our vertical velocity changes. And so notice, these are all those same equations that we had before, but I've added in a bunch of y's here. So our final vertical velocity is equal to our initial vertical velocity plus our vertical acceleration times our time. And probably worth noticing that AY in all of these equations is just going to be negative 9.8 meters a second squared, right? Okay? And then the only equation that ties them together is the Pythagorean theorem, right? This is a squared equals b squared plus c squared, right? Your v is just equal to your vx squared and your vy squared, right? Okay? I said that badly, but it's just Pythagorean theorem. All right? So